right, so we're near the end of class, but want to fit in the scenario that I had not recorded earlier. So we got cannonballs fired at, okay, so some blast speed, at an angle of so many degrees above the horizontal on a flat plane. Can you figure out horizontal component of velocity, initial vertical component of velocity, the time it took for the cannonball to reach the ground, and how far the cannonball traveled horizontally before striking the ground, based on nothing except for its blast speed and the angle that the cannon was turned. Oh, and also, gravity. Let's say this is on Earth. So Earth gravity. So I'm going to draw this picture out. And we'll make some. Now, there were a bunch of questions about component vectors that led up to it, but all the questions I asked were, well, you'd have to answer those anyway in order to get the answer. Okay, so I've got a cannon. It's blasting this cannonball. Plus B blast. I need a number, so let's say 100 meters per second. Just gotta make up my own numbers. Okay. And let's have this as a 40-degree angle above the horizontal. Okay. 100 meters per second, 40 degrees above the horizontal. Okay. Now the first two questions I asked, this is number 11 through 14, was what are the components of that blast speed, that blast velocity? So it's going kind of to the right and kind of up. But how much to the right and how much up? Oh, well, this is something that you guys have been doing for several weeks in this class, okay? Breaking vectors into components. Because this leg right here is equal to what times what? 100 meters per second times sine or cosine of 40 degrees? Cosine, yeah, because it's adjacent to, this leg is adjacent to that. Okay? And then this side here must be 100 meters per second times sine of 40 degrees. So let's see what those are. What is 100 cosine 40 degrees? That's 76.6 meters per second. That's that's v sub x, I should say. V sub x is equal to that number. And then this other number, if I pop in a sign, is 64.3. So this is v naught y. Okay. Now, that's velocity in the y direction, but also initial, because remember that's going to immediately slow down because gravity is going to start pulling down, which is not true for v sub x. V sub x stays the same all the way across. So anyway, this comes out to 64.3 meters per second. Okay. So there's your v sub x and your v naught y. Okay. That'll get us started. Draw the path that this ball takes. This ball is gonna, break out purple for this. Okay. Here's the actual path. It's gonna follow this parabola. It's gonna land somewhere way downfield right here. Something like that. The next question says, how much time did this whole process take? And you need to answer that to get the very last question, which is, what is this distance? Like, this is also called range, right? The horizontal displacement. So let's get both of those in that order. First, how much time, and then how far. Okay. Now, there's several ways you can figure out how much time this takes. Okay. One way you could do it, here, I'll write some down and then I'll just pick one of them and we'll do it that way. Okay. One way you could do it is you could say, well, I know that y is equal to v naught y t, let's say minus 1/2 gt squared if you blast it upward, but gravity's pulling down. Okay. And if you go from the ground back to the ground, then what is the what is the vertical displacement equal to from the ground back to the ground? You guys see it's a difference of 0. Okay. Vertical displacement. You could call this 0 meters, and you could factor out a t so you could avoid quadratic formula, and then you could solve for t that way. Okay. You can do that. Another way you could do it is you could say, well, however fast it's going here, doesn't it go slower, 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 and then faster, 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 faster? Do you guys think it has equal speeds and equal elevations? So however fast it's landing, it was blasted at the same speed. And the components would also be the same. So here's what I'm trying to get at. The final velocity in the y direction is equal to initial velocity in the y direction minus gt. But this number have the same magnitude, just one's the opposite of the other. Like one's going up and one's coming down, but they're the same magnitude. Right? And the third way you could do it is you could actually cut this problem in half. You could go from the cannon, say, to the top, in which case VFY would be equal to 0. right? Vertical. And you can solve for time, but then you got to take the time and double it for the total hang time. Okay. I'm going to play off the last thing that I wrote. I'm going to play off this one. So I know that it was blasted straight up at 64.3 meters per second because we figured that out already. That means that it's going to come crashing down also at 64.3 meters per second, but negative because it's going to be coming down. And its speed is changing at a rate of 10 meters per second squared towards the ground. This is all vertical for some time. Now this time represents the full hang time. Okay. Again, this is one of 3 different ways I just told you guys you could possibly get this. So subtract off 64.3 with 64.3 minus 64.3, plus negative, whatever. Negative 128.6 meters per second is equal to negative 10 meters per second squared t. Divide by size by negative 10 meters per second squared. It's my algebra step in pink. That will give you a hang time of 12.86 seconds. 12.86 seconds. Okay. All right, now that you know what the hang time is, how much time to get from the ground back to the ground, and you know its horizontal component of velocity, that's this number, all we have to do is multiply this together. It was going this fast horizontally for this much time. Okay? So, new paper. Okay. So how far did it go? X. We'll label it real fast. We'll do is light blue color. This distance x is equal to speed in the horizontal direction multiplied by time. And the speed in the horizontal direction was 76.6 meters per second. And the time, the total hang time, we found to be 12.86 seconds. 12.86 seconds. Okay. Now, realistically, that's way too much precision, but that's okay. I'll say rounding for the end. What is 76.6 times 12.86? Okay. I'm looking at the range is 985 meters. Ooh. Okay. So that problem involved a bunch of little steps, but nothing that's really new. And if you master that, if you're able to beat me to the answer on that, then yeah, you should feel confident that you are able to solve that. And so just to recap what you saw, we know the blast speed of a cannon and what angle above the horizontal it was turned, and what the gravity field is, right? So we got 10 meters per second squared straight down. Okay. That's all you need to figure out how far it went, the range. Now there was a bunch of little steps to get to that point. First thing you had to do was break the blast velocity into horizontal and vertical components, just cosine and sine. Okay. Then you had to figure out how much time it took to get back to the ground, total hang time. I told you 3 different methods to do it, and I just picked one and solved for the time and got about 12 or 13 seconds. Okay. And then finally, figure out how far it goes, the range. Just take the horizontal component velocity, multiply by the hang time, and that's how far it went. Boom, boom, done.